All right, we can get started. Well, thank you everyone for joining. This is our webinar on wearables and AI for precision health. So here, Asif, Ramesh, Prisha, and I, we will present some of our recent works on how to use wearable technologies and machine learning for health monitoring and clinical interventions. So agenda for today includes, first I'll talk a little bit about motivation for this research and what it means, and then Asif will talk about some of his work on precision nutrition with wearables, and then Prisha will discuss her work on predicting glucose response, and then Ramesh will talk about stress monitoring project, and at the end I'll talk about some of the research opportunities that are available within Washington State University, within Arizona State University, and beyond. Okay, so motivation for research is the increase in prevalence of chronic conditions. In fact, 60% of American adults have at least one chronic condition, and many have more chronic conditions. And in elderly population, the situation is worse. 80% of them have at least one chronic condition. And the burden of chronic conditions is quite high. In fact, we spend up to 86% of our healthcare spending on chronic conditions, and in the US we spend close to 18% of the GDP on healthcare, which is twice the amount of spending with respect to GDP as some other countries like UK. And in the US, for example, we're spending a total amount of cost, total amount of spending on healthcare is actually $4.3 trillion a year. Right? So this is also, despite the fact that a majority of chronic conditions are preventable or they can be delayed. And the idea here is, how can we go from an acute care setting, which is reactive, to basically, which is called a reactive care, meaning that you're waiting until you get sick and go to hospital, to scenario where you can provide care everywhere at any time, okay? And basically mobilizing care, and that way you can reduce the cost and improve the quality of care. So in Embedded Machine Intelligence Lab, we design wearable systems and AI to monitor various health conditions. So these are some of the biomarkers, or basically some of the technologies that we use, and some of the outcomes that we monitor. That includes activity, behavior. We do research on diet and nutrition. For example, here you see a smart bottle that has embedded sensors in it for fluid intake monitoring. Asif and Prisha will talk about some of the projects that we have here. Medication adherence monitoring is another area. Glucose monitoring in people with prediabetes and individuals with diabetes is another area. Stress monitoring, Ramesh will talk about some of that. And gait and mobility assessment and is another area of research in our lab. So with this very brief introduction, I'm going to kind of ask Asif to continue the discussion on precision nutrition. Asif, take it away.
Thank you, Dr. Hassan. I think you guys can see my screen.
Yes.
Okay, perfect. So yeah, I'm Asif Arifin, and I'm doing my PhD in biomedical informatics program at Arizona State University. So I'd like to start with some facts. As you know, and as you can see, almost 2/3 of all the deaths in 21st century is happening only because of diabetes, cancer, and other chronic conditions. And as Dr. Hudson said, the United States is spending almost like $4.1 to $4.3 trillion annually for treating these problems. But as you know, we can fairly reduce this cost by maintaining proper diet, reducing fats, carbs, and salts in our daily consumptions, and also by ensuring a healthy lifestyle. So, driven by these facts, I'd like to, employ my knowledge on AI, on diet, and on data collected from wearables. So I would like to say that broadly speaking, my research has three different directions. Data scarcity. I know that when we try to do research in this specific domain, we don't come up with so many data sets publicly available. So I'm trying to identify how we can reduce the problem of data scarcity. And once we have data, I'd like to identify problems that are related to our health by doing some assessment. And when there is some identifiable factors and, a health problem can be, identified, then I go for, interventions using other techniques based on AI. Okay, so starting with VERT, which is Virtual Teacher Support for Effective Active Multitask Active Learning. So here we'd like to answer, can we increase the efficiency of multitask active learning further so that we can reduce its dependency on labeled data? So in this case, we incorporated this virtual teacher or VERT to the baseline multitask active learning network. So this VERT, along with the Oracle, will keep annotating unlabeled data for an effective training of the central multitask learning model. So as you can see, the yellow bars are coming from a baseline multitask active learning network, and the blue bars are coming from VERT. And we are getting an edge over the yellow ones. Moving forward, I talk about Glycinth, which is an autoregressive framework for glycemic data synthesis. So, the very state-of-the-art or cutting-edge technique to synthesize data will be using a GAN or a diffusion model. But since we are limited in terms of data, I'd like to introduce an autoregressive framework to synthesize data, to be specific, to synthesize CGM data. And we compared our results with some statistical validation. As you can see, the distribution of our synthetic data is pretty much the same as the real ones. And also we fed the synthetic data in a downstream task, which is, to estimate the meal macronutrients from the synthetic CGM signals. So as you can see, the synthetic data is giving some sort of similar performance compared to the real ones. In some cases, it's giving better performance. By the way, CGM is a continuous glucose monitoring data, which is, a sensor that transmits our blood glucose level once in maybe 2 or 5 minutes. Okay, so then I would like to talk about a user study I'm also doing. I understand the fact again that we are left with very small amount of data in this domain. So I recruit participants, feed them with all these sensors, and I collect this heart rate, galvanic skin response, temperature, accelerometer data, glycemic response, and other stuff as well. And we are feeding these participants 5 times in day, and you can see it's reflected on his glycemic response. And with the blue and red bars, I'm collecting positive and negative moods from the participants. Moving forward, I would like to talk about a health assessment problem where I tried to answer, can we predict hyperglycemia in advance with some sort of explanations. So I incorporated information from a person's meal macronutrients, his current blood glucose reading, and also his insulin information, and fed them to a decision tree-based model and to understand whether he'll have hyperglycemia or not within the next 4 hours of consuming that specific meal. So the data set we have here is from 5 subjects, and we have access to their meal macronutrients, insulin information, and glycemic response as well. We compared our approach against SVM, and for both of the cases, you can see we're getting 81% accuracy. But decision trees come with some sort of explanation, so we agreed to move ahead with decision trees. So in addition to the decision trees, I'm also using a wrapper function, which we are calling recursive feature elimination, or RFE, which gives us access to top 2 contributing features for a person's chances of having hyperglycemia. So here are the decision trees. We can use them as explanations as well. Like for this person, he's going to have hyperglycemia if his carb amount is consumed carb amount is less than 83 grams, fat is less than 1.5 grams, and carb composition is above 68%. But as you can see, it's not possible to, it's not comprehensive, because from here we can say that we can control his chances of having hyperglycemia by giving him an extra dose of insulin, or by keeping him waiting for some time until his blood glucose level comes down to certain values. So that's why we are coming up with a new solution, which is an intervention based on explainable AI, where we try to answer, can we modify the current view of explainable AI for precise behavioral intervention? So here, we are trying to come up with a deep learning based approach, but deep learnings are not good enough for explanations. So we try to increase the explainability of the deep learning model beyond that of the decision tree and linear models, so that we can come up with precise health interventions for behavioral modifications. So as you know, deep learning networks come with decision boundaries. So if we can access the decision boundaries, we can use it any way we want to generate customized suggestions and for interventions for any user. So let's assume these reds are hyperglycemic samples, greens are normoglycemic samples. Our neural network will define a region for both of them, and then we will create adversarial, synthetic samples along the decision boundary. And once we have them, we can forget about the real data. And now for any hyperglycemic person who is, the purple star, we can force him within the green region, so that he will have lower chances of having hyperglycemia. So once we are done with the technology, we'd like to implement it on a smartphone, and also the smartphone application will tell us whether a person is going to have hyperglycemia or not. If he is going to have hyperglycemia, we'll tell him that, hey, you're going to have hyperglycemia, so reduce your carb amount by 20 grams, or wait until your blood glucose level comes down to a certain value. I would also like to talk about dietary intervention for consistent weight reduction. And I present Bob here, who is an obese guy, but he wants to get into a good shape. He talked to his dietitian and got to know that he needs to reduce his consumptions. So he made a plan. This is where our algorithm will come into play. So we'll create customized list of food items and their corresponding amounts throughout the plan period, so that we will help Bob reach his goal by gradually lowering his consumptions, and he will reach his goal in terms of calorie and also in terms of his weight within the given time frame. So yeah, I'd like to leave the floor for Prisha. Thank you for listening for me.
Okay, are you able to see the screen?
Yes, we can see that. Go ahead.
Okay, yeah. So today I'll be presenting my research titled Glucose Assist, which is this novel personalized system for prediction of an individual's blood glucose levels, and then also identifying dysglycemic events early using those artificial intelligence neural networks. So I think Asif also mentioned this, but basically 537 million adults have diabetes globally, and the number is expected to increase to 643 million by 2030. And diabetes is one of the world's fastest growing chronic diseases. So normally, in an individual's blood glucose levels, or normally in their systems, when their blood glucose levels rise, then the pancreas will normally release insulin, which will then signal to the liver to take and convert that glucose into glycogen, which will then leave an individual's blood glucose levels in their normal range. But when this process does not work in an individual, it leads to that hyperglycemia, or that unnatural spike in an individual's blood glucose levels. And we see a similar thing when an individual's blood glucose levels drop. It leads to hypoglycemia. So, and some of the effects of those, Asif also briefly mentioned this, is like seizures, loss of consciousness, and potentially even death. So one of the things is that there is a need for this personalized solution to help these individuals manage their blood glucose levels in a personalized manner. So some of the current research that has been conducted utilizes limited input parameters. These models are data hungry and computationally expensive, which make it hard to implement like with an app. And then it also lacks that prediction of those dysglycemic events like hyper and hypoglycemia. So some of the objectives for Glucose Assist was to help these individuals manage their blood glucose levels in a personalized manner. Ideally, it would help them predict their blood glucose levels for the next 30 minutes, and then predict and notify them if there would be a future hyper or hypoglycemic event, and then predict their blood glucose levels based on a potential meal that they want to consume, and then give the user with preventative measures so they can take action. So there are 4 main steps to Glucose Assist methodology. First was data pre-processing, then model building and training, then was the prediction and identification step, and then we went on to analysis. So in this first step, the data set, I utilized the Menly data set, which contained 20,040 CGM records of 167 meals from 5 different patients. And Glucose Assist also takes an individual's diet, health, and medication data as input, because normally these are factors that affect their blood glucose levels. For example, like carbohydrates generally are seen to lead an increase in an individual's blood glucose levels, and insulin for those diabetic patients leads to a decrease in their blood glucose levels. Then I did time series forecasting. Time series forecasting is the process of utilizing time as a variable to make accurate predictions for the future. So one of the things that I did is to process this data set for time series forecasting. I developed this automated framework. And what it did is it split the data set into a 3D array of time steps, the samples, and then the features. And then Glucose Assist also split the data set into 60 minutes of input and then 30 minutes of output. Then after that, I used like the multi-model approach. So the 2 different networks, or the 2 different parts to Glucose Assist, was first the convolutional neural network, which basically was for glucose level prediction for that horizon of the next 30 minutes, and then also utilizing the random forest classifier to predict these glycemic events in the future. And so I went through multiple different iterations of this convolutional neural network before finally settling on one that used the convolutional layer, the maximum pooling layer, the flattening layer, and the dense layer. And then a brief overview is that it basically, a convolutional neural network utilizes a series of filters to extract different features from the data, and then utilizes these to make accurate predictions. And the random forest classifier utilizes a series of decision trees, which is similar to like yes or no questions to help it reach the most accurate result. So the design of Glucose Assist had 2 main phases. In this first phase, we take the individual's health, diet, and medication data as input to the CNN model. Then it predicts the blood glucose levels for the next 30 minutes of that individual. And then utilizing the random forest classifier, it'll predict future hyper or hypoglycemic events. And then if there is one of those, then it will provide the user with some preventive feedback, such as go for a run or then eat ice cream. In phase 2 of Glucose Assist, let's just say that the user wants to eat ice cream, for example. Then they can enter this information into Glucose Assist, and then ideally, it would be able to tell them that you will reach a hyperglycemic event at this time, so instead you should eat an apple. So for phase 1, my app design that I've been working on As we can see, so first it'll take the individual's current glucose levels, and then it'll make a prediction for the next 30 minutes. Once it does that, it'll also provide the individual with the hyperglycemic event and then also preventative measures. In phase 2 of Glucose Assist, what it does is it first takes an individual's, and here's a little demo. So first it'll take an individual's current blood glucose levels and give the next 30 minutes of prediction. Then the individual can choose for like a potential meal-based prediction. And then right now they can select from a series of different food items. Let's just say this user wanted to eat ice cream. Then when they predict that, you can see how it'll give them the current predictions and then the meal-based predictions. And with these meal-based predictions, the individual would hit that hyperglycemic event. So it'll then provide them with a food that has a lower carbohydrate value. So some of the statistical analysis to like quantify the performance of Glucose Assist that I did was one tuning the epochs. Epochs are the number of times that the model is able to see the data set. And a general trend notice is as the number of epochs increase, the root mean squared error decrease. And root mean squared error is a metric that is used similar to accuracy, and the lower the root mean squared error is, the better. I also did a comparison between the convolutional neural network and then a long short-term memory network, as both of these can grasp the time series data. However, one of the trends that I noticed is that the convolutional neural network performed much better on this data set. And after doing some research, I realized that convolutional neural networks work better with smaller amounts of data and extracting those features, whereas long short-term memory networks need larger amounts of data. Then another thing that you can see here is also the an actual versus predicted graph. The blue is the actual values, and then the turquoise was the predicted values, and then the orange lines were the hyper and hypoglycemic events. So Glucose Assist is generally able to predict those hyper and hypoglycemic events. However, there's still a little bit of fine-tuning necessary. I also utilized a Clark's error grid, which shows the difference between the actual concentration or the blood glucose levels and then the values predicted by the model. And the majority of the values fell in this zone A and zone B, which is considered that clinically accurate and then clinically acceptable values. Then for the random forest classifier, I also utilized hyperparameter tuning. Originally, I had tried to do this hyperparameter tuning manually, but then I noticed that there was a lot of variance in the results I was getting. So then I utilized grid search, which is a model hyperparameter optimization technique to tune these different hyperparameters. And so then Glucose Assist was able to get an accuracy of 97% for identifying those dysglycemic events. I used the confusion matrix, which is very similar to the Clark's error grid, where it displays the actual and predicted values. So the conclusions of the research that I conducted was that it is possible to design this multi-model system that can predict an individual's blood glucose response in real time for the next 30 minutes, and then also based on a potential meal, utilizing an individual's diet, health, and medication data. Glucose Assist was able to attain that root mean squared error of 1.23 and a 97% glycemic event identification accuracy. One of the key points, though, was that it was able to demonstrate the feasibility of developing the solution that can make predictions with a smaller data set. Because Glucose Assist was designed for personalized to each individual, so it took 10 days of training data and then was able to accurately make these predictions. And so as a result, this model is not data hungry or computation expensive, which makes it easier for app deployment. And then, of course, it has the potential to positively impact over 911 million people's lives who are faced with diabetes and pre-diabetes globally, who need this easy-to-use and personalized solution to help them manage their blood glucose levels. Yeah, thank you so much for listening to my research.
So, well, first of all, thank you, Asif and Tushar, for presenting your research. It was really interesting. And next, I'll talk about another aspect of research that our lab conducts. So, until now, you have heard about how in different projects we are tackling with issues with physical health. Next, the another component of the holistic health of an individual is mental health, and stress is in general considered a very important component of the whole mental health paradigm. And in the next few slides, I'll talk about some projects that are related to stress. And just to give you an overview about stress, stress in general is experienced by almost everyone. And the reason behind the stress could be many different types, right? But ultimately, stress, when it is affecting an individual all the way in the brain, stress responses are basically governed by two different components of the what is called autonomic nervous system, right? And these components are shown here in the right part. The first one is called sympathetic, and the second one is called sympathetic. And the important component is the sympathetic component because it actually drives the changes in our body that affects the stress that an individual is experiencing. These changes, one of the important changes, our surface of the screen starts innervating and we sweat. And there are many different ways we can measure this process. And one technique is to measure the conductivity on the surface of the screen. And for this, we can use a device called Embedding Machine Intelligence Lab. It basically measures how your skin conductivity is changing. And another measure of stress is heart rate, right? So in general, during a stressful situation, our heart rate goes up. And from the signal that is used to compute heart rate, which is called PPZ, we can derive much more granular information from heart rate variability, basically how every beat, every consecutive beat of heart rate is varying with respect to time. And the information from skin conductance and heart rate variability can be used to assess and quantify the stress level of individuals. And one of the another very important aspect of stress is that stress is very detrimental towards individuals who are already suffering from another kind of ailments. And one such population group is individuals suffering from alcohol use disorder and alcohol use disorder, right? And in terms of the significance of the problem, AUD, alcohol use disorder is a very huge problem in healthcare, and in terms of the deaths that are governed by it are huge, and also how people are affected, the number of people, more than 14.5 million people, right? And another important aspect of stress is that when someone is addicted to alcohol and is trying to, refrain from drinking alcohol and going through a rehabilitation program, most often stress is the driving factor which causes them to relapse, right? So in general, if we can think of a system that can actually detect stress in real time and then provide nudges or what is called just-in-time intervention to such an individuals, then we can guide these individuals toward positive behaviors. And in the case of individuals suffering with alcohol use disorder, we can prevent them from relapse, right? So to study these associations and quantify how successfully we can do that, we design a study to actually measure the number of alcohol drinks an individual were drinking during the day. We collected their sensor data, their biomarkers using different kind of sensors. And to summarize, there were three components in the study. One was what is called ecological momentary assessment. It is basically a survey that is sent out to your digital devices. It could be your phone or your tablet via internet. And in the survey, it will ask you about your mood, your stress level, and many other factors. The second component was a sensor, which is Embedding Machine Intelligence Lab. It basically measures your biomarkers related to skin conductance, heart rate, and surface temperature of your skin, and also your movement data. And the third component in the study was interview sessions that were conducted along the study life cycle and also at the end of the study. And using the data that we collected, we did some statistical analysis to establish whether we can actually, whether there is any association between the stress events that the participants expressed via the survey and also by pressing the button on the sensor device. We found that the EDA signal, which is EDA is basically skin conductance, electrothermal activity, were positively associated with the number of stress events, and also the hardware variability features, HRV features, were also significantly and positively associated with stress events. But we didn't find any associations between hardware variability and EDA features with respect to alcohol use and also alcohol trading. So these results were much more of a statistical analysis. And next was to use the sensor data not from our study, because our study had a problem with the data quality and also the lack of labels. We used the open source data set to actually build a model, a machine learning model that can use raw skin conductance data without any feature computation and selection, and then predict whether someone is stressed or not stressed, right? And we also study what we call subjective nature of stress with our leave on subject analysis. And the subjective nature of stress stems from the fact that a same external stimuli, for example, watching a horror movie, can be a very stressful situation for someone, but not on the same level for someone else, right? So the effect or the response a body or individual shows to us an external stimuli in terms of stress is very subjective in nature. And it is very, I think the subjective case is very common across the spectrum of different healthcare problems, like Trisha was saying earlier. And in terms of the stress analyzer, which is the model that we're following, it has three different components to begin with, right? The first part is choosing the best modality to actually do the model building process. The second is after you have selected the best modality, you do the model construction, and then finally you do the model personalization to account for the subjective nature of the stress. And in terms of sensing modality and sensors, again, we have been empathic info. And the model architecture is a very simple model architecture, just one convolutional layer followed by three different fully connected layers, and in between drop-off layers and maximum layers. And then finally, we have personalization in an online training paradigm where a user is using a system and the system is being retrained while it is being used on the data that is generated for the specific user. In terms of performance, we have three different classes in the dataset: baseline, stress, and amusement. And this table basically lists out the accuracy and F1 score. For binary case of stress and not stress, the model was found to have a high accuracy and F1 score. But with three-class problem, baseline, stress, and amusement, the performance declined. And this is again, I believe, attributed to the fact that when we split the data set into two different groups, the number of training samples decreases, and it is again shown reflective on the performance of the model. And comparing our model with other stress detection or classification systems that are feature-based, basically it computes a bunch of different statistical and other informative features from different modalities, and then use the computed features to train different types of machine learning models. If we compare our work with these approaches, then we find our work to be quite competitive with what is the state of the art right now. And one thing to note here is that we don't compute any features. We use the raw data after some pre-processing like filtering and such. And without any feature computation, the model that we trained was able to achieve similar level of performance. And next, in terms of personalization, we can evaluate that with what is called a leave one subject out analysis. So basically, you train your model on the data from all the subjects except one, which you keep for testing. And if we do that, we see that for many, if you look at the crimson bar here, for many subjects, the x-axis is the subject indicator on for the test set. We see a sharp decline compared to the training set, and this is again, we believe indicative of the subjective nature of the stress and also the differences between different individuals. And to account for that, we retrain the model on the subject data again. And after retraining, we saw a huge improvement in terms of accuracy for stress detection. And this shows that even after you have a model, a general model that you have trained, it makes sense to actually personalize the model in some way. Maybe it could be an online learning paradigm or something else to actually boost the model performance, and also so that the model is much more has better knowledge of where it is working, when for whom it is working for. And yeah, so until now we talked about how stress is very important, how we can detect the stress. The other component is that once you have detected the stress, what you're going to do about it, right? So then the question of intervention comes in. And there are many forms of intervention in terms of the stress, and one form is a very wide area of research and very established, I would say, area of research is listening to music. And I think we all of us have some experience regarding this. So listening to music is in general considered to be an activity that is associated to decrease level of stress. But listening to music can happen at different stages during your stressful situation. So you start to get stressed, then you reach your peak, and then you finally slowly get decline. So depending on where you start to listen and what or when the music is employed, it could be categorized into three different categories: anticipatory, regulatory, and managerial. But in general, all of these three things are working towards the same goal of decreasing the stress level of an individual. And in terms of what we were thinking of a system where you have sensor data and also some other information from the context of the individual. And you have some machine learning system, for example, the convolutional network that I talked about earlier, that is detecting whether someone is under stress or not in real time. Maybe this model is on your phone. And then depending on the outcome of this model, the system recommends some intervention or action so that in the proposal, intervention and action helps an individual manage or regulate his or her stress level, right? And to establish or to determine whether this is possible or not, and also to understand the different facets of it, we conducted a study where we recruited individuals to participate in a first online survey, and then coming for an hour-long session in the lab where they were asked to wear the empathic lighting for which one to record different markers, and then listen to music of their own choice and complete two different tasks designed to elicit stress. And during the in-lab session, the participants also completed a set of questionnaires that is designed to record emotional state and create anxiety. And we are still in the phase of actually doing the data analysis, and we'll be publishing our results soon. And then I'll be able to talk more about what we were able to achieve. But summing it all up, and this is what a system or a mobile health system for stress detection and intervention looks like. So you have data from many different sensors again, and then you have some machine learning happening or some sort of other algorithmic optimization happening that can do stress detection, context information, and then you have intervention mechanism. And one of them that we are experimenting with or analyzing is listening to music. There could be another thing, for example, like chatting to an AI agent, which seems to be very feasible given the current context of natural language research. And so more other type of interventions are possible. So this sums up everything I have in terms of the stress and what our lab is doing. I will now pass on to the person.
In the next few minutes, I'll briefly talk about some of the research opportunities. And the main reason we want to discuss this is because oftentimes high school students, community college students, and undergrads are not aware of research opportunities out there. They don't know how to look for those. We're hoping with this we can help a little bit. An example is this research opportunity as Arizona State University Sense Program, where actually Prisha, who presented today, she's actually a senior intern. This is an opportunity for high school students to come to ASU and work with a faculty in a research lab and conduct research. So this is an opportunity. So you can just Google for this program, or go to this link and find out more about the program eligibility and so on and so forth. Or you can email us. We'll be happy to help. So another opportunity at ASU is this undergrad research in general. It says if you search for undergrad research at ASU, so it takes you to this page or similar where you can figure out more about opportunities at ASU. So this page in particular is focused on NSF RU programs, and we're going to talk about them a little bit in a second. And it tells you how to basically navigate the website, how to find the research opportunities and apply. So this one is summer research programs at Washington State University. Actually, if you go to this link, it will take you to the page where you can see the up-to-date information about available opportunities at Washington State University for undergrads. I think this screenshot is from 2-3 years ago when we offered our first remote, I believe, RU program at Washington State University. And NIH Undergrad Training at Washington State University. This is another. So NSF is not the only program that offers basically or funds undergrad training. NIH is another. If you go to this link, that's one example of NIH funding and programs within a university. This is the WSU program. My colleague, Dr. Dan Cook, actually leading this project. It's a collaboration between School of Electronic Engineering and Computer Science and also Department of Psychology at Washington State University. Now, National Science Foundation provides RU or research experience for undergrad type of kind of funding, and you can search even if you Google NSF RU, it will take you probably to this page where you can search for different RU sites, which mean different basically programs, different funded projects at different universities, and in there you can just skim through them, look at different opportunities, see if it interests you, and apply. Once you go to the page specific to different programs, for example, here, computer and information science and engineering. So that's the link I chose. Then it takes me here. It shows all RU programs in alphabetical order here. That's why ASU is shown first. But you can see a lot of these active projects that you can read about. For example, this also involves, this first one involves also wearable and flexible sensors, machine learning, so which is relevant to some of discussions that we had today. If actually today I downloaded this file as a, I guess, CSV file, and if you want, you can just scan this code and it take you to the downloaded CSV file. Like put it on a public Dropbox folder for whoever wants to access it. But regardless, you can go to the NSF website and look at these. You can download and then search for those if it's difficult to look at it in a browser. So with this, we're going to be kind of finishing our presentation. We'll be happy to take any questions you may have. Thank you for listening to this video or participating in our webinar.